Good afternoon, everyone. On the behalf of Nihon Kone, I would like to say thank you for coming here. It's a huge pleasure to us to have this section here today with Professor Marcelo Amato. And we will discuss some features and some physiological background about the respiratory muscle pressure and protective lung ventilation. Thank you.
So the idea of this demo box is to discuss a little bit about the problems of muscle pressure. It's a topic that has increased interest in the last years, and especially triggered by some big controversy in the last weeks. I have some disclosures here, but it's not going to affect the content of this presentation. So the concept of driving pressure was well established. I think after the publication of this paper, we have more than 50 papers showing the same thing in different populations, in patients, in post-operative patients without any lung disease, and always there is a correlation between driving pressure and mortality. And the correlation is so strong that if you compare the strength of this correlation, it's the same strength as SAPS. So if you think about the minimum SAPS and the maximum SAPS, it's the same impact of this minimum driving pressure to the maximum driving pressure. So no other parameter at the bedside is so important as this, except for age. Age is the only one that's a little bit stronger. In the last weeks, we tried to understand a little bit better if in this graph there is a threshold, because I was obliged to remove any indication or suggestion of a threshold when we published this. But in our original formulation, we had the impression that there was a threshold around here. And this graph, when we put this line here, is just the average of the population. Doesn't mean that 15 is the threshold where patients are protected and here not protected. So then we tried to go deeper in this, and we used the same data bank now with some new data, and then it was very clear that there is a threshold. And by doing piecewise regression, in which the algorithm tries to find automatically some threshold, everything indicates 12. And 12 is a good number because we have some experimental data suggesting the same thing. It's where you start to see some increase in cytokines, pro-collagen. So looks like that this is the threshold for normal animals. So you are doing 2.5 times your normal driving pressure. We here are using 5 of driving pressure, so when we exceed 2.5, it's a threshold that we start to have some degree of lung reaction, fibrosis and inflammation. By many different criteria, it's always suggesting that 12 is the number where you start to see some problems. Doesn't mean that you should use this clinically. But you have to think that you can only be 100% safe if you are below this number. This is for normal patients. We have also in more than almost 100,000 patients the same threshold. So it looks like it works for normal patients or for patients with lung disease. Then there is this big question. Is this valid for spontaneous ventilation? And this is a very important question because, you know, there is a kind of religion surrounding this. Just to give you some example, do you remember about this? This was during the COVID time. Martin Tobin was having a big discussion with Luciano Gattinoni. And the topic of the discussion is that Martin Tobin was saying that patient self-inflicted lung injury was a kind of illusion, was a concept that was created without any proof. And on the other side of the the debate, we had Luciano Gattinoni. It was very hot debate. If you follow this debate, so in a couple of weeks, they published each one almost 10 or 15 editorials, one arguing against the other. And Tobin was making the case that the evidence for patient self-inflicted lung injury is very poor. And recently, last week, he published this review. So patient self-inflicted lung injury, does it really exist? And he was making the case that because of this idea, patients during the beginning of the pandemic, between March and April, they were more intubated unnecessarily. And then he says that the hypothesis of Pesili was unfolded just because of an editorial, just because of an opinion of Laurent Brochard and Pesenti, and it was not based on any good scientific data. My point today is to say something completely different. My argument is that if we believe that VILI, ventilator-induced lung injury, is accepted, then PSILI, patient self-inflicted lung injury, must be accepted beyond any doubt with an even higher degree of certainty. Because it occurs in athletes every day. Marcelinho can tell us a little bit about this. For equivalent transpulmonary pressures, it is pure physiology. Transvascular pressures are much higher during spontaneous ventilation if you compare with controlled. You have increased venous return, so you have more edema. And we have Pendeluft, so the diaphragm is always less gentle than the ventilator. This is crazy because everyone believes the opposite. Everyone believes that the ventilator is bad, spontaneous ventilation is good. It's completely the opposite. And this is very deep science, and there are very good data supporting this. I think the first person that took a very scientific approach to this was Brian Kavanagh. Unfortunately, he died during the pandemic. And he was trying to prove that negative ventilation was better than this. Sorry, the speed of the respiratory cycle is different, but just because of the movie. But what he was trying to prove is that you have less tidal recruitment here than here. But look at the picture. It's exactly the same. So he was trying to prove that this was better, and he could not. Then, the first paper that he published on the topic was trying to say that negative pressure ventilation, spontaneous ventilation, is fundamentally different from positive pressures because it results in better oxygenation and less lung injury. But then Stephen Lorig wrote a letter to him, myself also, and then we requested some data, additional data from the experiments. And we were suspicious that the setup was different from negative and positive, so they were not equivalent. Stephen Lorig visited his lab, they tested, and they found a mistake. They found a mistake because the Curus, where you were doing negative pressure ventilation, was measuring the pressure in the wrong place. When he put the sensor very close to the chest, then he realized that by doing a fair comparison, negative pressure was worse. And then he tried to send back to the Blue Journal. Blue Journal didn't accept. Some journals, they don't like a retreat, that the investigator tried to retreat himself. So, but then he published in the intensive care a different perspective. Now, these data do not support major differences between negative and positive. This is a very scientific attitude. I am really proud about his attitude. And, you know, and this is very nice because if you look at the literature, sorry for this, but Martin Tobin was completely ignorant in what he was saying. And he's a monster. I feel bad about saying this because he's a brilliant person, the most knowledgeable guy, but he did this evaluation in a very sloppy way. For instance, the paper that he quotes, the Colobal paper, the famous Colobal paper, that he believes that this is not a scientific paper. He was having a very well-controlled experiment where he was injecting acid here directly in the brain, in the fourth ventricle, and then he had the three groups. Acid in the brain, stimulating the drive, so then they started to have 3 times the minute ventilation. The animals were alive, were kept in a jail and alive for 24 hours. Then he injected salicylate, and then he did mechanical ventilation. And guess what? These animals died, and these animals survived. And the reason is it's because these animals started to do for 24 hours tidal volumes of 15, respiratory rate of 60. And then after some hours, they started to have lung edema, decreased compliance, and at autopsy, the lungs were very heavy. It's not only this experiment. There are plenty of experiments in the literature. So this is why I think the argument of Martin Tobin doesn't stand. The famous paper of Didier Dreyfus. This paper was the trigger for our initial trial in Brazil when we did protective ventilation for the first time. And in this paper, if you compare positive pressure ventilation with negative pressure ventilation, look at this. This is the normal level, permeability, lung edema. Pink is worse. Negative pressure produces more edema. And then he tried to explain this. And then he tried to give dobutamine to these guys to increase the flow through the pulmonary circulation, even though he could not get the same results. This is something that we talked about the marathon runners. 40% of the marathon runners, after the race, they have beelines. Why they do not develop ARDS? Because they recover, it's first hit, but they have the injury. So this is a proof that this happens in normal patients. And you can imagine what would happen with a patient that has had already the first hit in the ICU. Takes 12 hours to recover, but some guys do not recover. This is a marathon runner. Some guys do not recover. Look at the X-ray. Because of this problem related to negative pressure ventilation or spontaneous ventilation, the Anglo-Saxon people from North America, they believe that volume control ventilation is much better than pressure control. And the very reason for this is because they believe that they can control transpulmonary pressures. Because, for instance, this is a controlled cycle, esophageal pressure, airway pressure. At the end of the breath, this is the transpulmonary pressure, okay? When you have negative pressure ventilation and you're using volume control, you do a negative pleural effort, and then you have some scooping of the airway pressure because you pull down airway pressures in a way that transpulmonary pressures, they seem equivalent. It's completely different from pressure control. When you do the pull down with your pleural pressure negative, now your transpulmonary pressure is increased and tidal volume increase. So some people believe that this is protective. So in a way, you are neutralizing the impact of spontaneous effort. But then Takeshi Yoshida came in and proved that this is wrong also. Why? Because he measured esophageal pressure and pleural pressure, and then he could show that pleural pressure is much lower than esophageal pressure because of the pendeluft. So you have local forces that you cannot capture with the esophageal balloon, which means that whenever you are doing some effort, you are causing problems. There is no way a strong effort can be, let's say, easygoing, can be something that is not going to cause any problem. Strong effort is going to cause problems always. If you are in volume control, pressure control, CPAP, spontaneous, whatever. Think about one extreme example. If you have croup, you have edema in your pharynx and larynx, and then you have an obstruction. The first description of the problems of this disease is lung edema, because sometimes you have almost zero tidal volume, but you are doing so much effort that you have lung edema. So you don't need a high tidal volume to make lung edema. This paper of Takeshi is very beautiful because he has some images to prove the case. This is a patient during volume control ventilation paralyzed. The amount of tidal recruitment is very low. A little bit of tidal recruitment, right? And then the patient started to breathe. Tidal volume was the same because the ventilator was controlling tidal volume. But look at this. Same tidal volume, same transpulmonary pressures, but much higher tidal recruitment. Let me go back for you to see. Because of these local forces compared to that. So no way, if you are doing strong effort, you are causing local pressures that can hurt your lung. This is beautiful because you can recognize this with EIT. This is a patient that was doing breath stacking. Big efforts. This is local stretch, ventral lung and dorsal lung. Then you say, oh, let me play with the ventilator. Let's increase the I time for the patient not to have the second breath. So then we did it. But look at this. 1 second. When we did it, initially, everything was the same, but after a few minutes, the patient was doing a big effort, and then he was stretching the dorsal lung regions, no matter what was going on with the ventilator, because he can do a local force. If you are not understanding very well what I'm saying, please go to the presentation about pendeluft. But pendeluft is a kind of situation in which the lung keeps the same volume, but you stretch the dorsal lung regions, and as a result, the ventral lung regions, they shrink. So the total lung volume is the same, but the dorsal region gets overstretched, and this is exactly what is happening here. This is why it's a must to record, to understand at the bedside how much force you are doing. So I'm not going to go over all this data. I'm just trying to say that Tobin was completely wrong. This is just a proof that spontaneous ventilation inflamed the lung. This is the same tidal volume, weak effort, strong effort. So whenever you have spontaneous ventilation, if you are using pressure support, you have to think about this idea. You have this negative force, you have the positive pressure force of the ventilator, and they sum up. It's not a perfect sum, because it's a perfect sum if this peak coincides with this peak, but sometimes there is some misalignment. But it's approximately this. Total is equal to what the ventilator does plus the muscle pressure. Now, something very important, because there are a big confusion in the literature. In this case, you could say total driving pressure is 30. But here, I'm taking the dynamic component. But think about this. Every driving pressure can be decomposed in an action of the muscles and an action of the ventilator. This is clear. We have talked about this. But each one can be decomposed also into resistive and elastic. When we talk about the driving pressure in the way we described in the controlled mechanical ventilation, we are talking about elastic. And then sometimes during spontaneous ventilation, people is talking about the dynamic, which is a little bit higher. Look at this. Dynamic, static, because this is elastic pressure. This is resistive pressure. The same for airway pressure. So dynamic driving pressure is always a little bit higher than the static one. Typically, when you have a patient with ARDS, elastic is about 80% or 90% of your driving pressure. So it's not that far. But this is important to think about when you are considering the numbers. So in this case, the same example, the static component would be 27. So, and then you can do the same sum. Ventilator is static, plus patient is static driving pressure, which is exactly this. When you're talking about driving pressure and mortality, we are talking about the static, and in this particular case, it was the ventilator component. But I took 20 minutes to prove you that it doesn't matter if the ventilator or the patient is the same, and even worse if it's the patient, because of these problems of transvascular pressures in lung edema. So how we monitor at the bedside? Typically today, there are three proposals. The first one is to compute compliance daily, and then you say, then you divide tidal volume by compliance. This is my preferred approach, because whenever I'm in doubt, this is unequivocal. You know for sure that this is true. For instance, you have this scenario. You have a compliance of 12 that you measure because you gave a bolus of paralysis and sedation. You measure compliance is 12. Then we always assume that this is true, and we can assume that driving pressure is tidal volume divided by compliance, which should be also this. 360 divided by 12, 30 of driving pressure. It's a lot. It's exactly what is happening here. You know, I get mad every day in my ICU when I see a situation like this. You know, from the resident perspective, this is wonderful. My tidal volume is 7 mL per kilogram, so it looks okay. I'm using 15 of pressure support. Maybe there is some resistive forces. But look at this. The muscle pressure is 15. And this ventilator, for instance, is telling us explicitly driving pressure is 30. Let's go a little bit deeper, how it's calculated. So this patient has 80% mortality just by receiving this ventilation. 80% mortality if he has ARDS. This is what the graph is telling us. So the second way is to do the occlusion pressure, expiratory pause, and then you can have also inspiratory pause, expiratory pause, and we can use the esophageal balloon. But now, I would like to introduce you that now the new ventilators, they calculate muscle pressure even without the esophageal balloon. And this gets much better because esophageal balloon is very tricky. You have all sorts of artifacts and problems of calibration of the volume inside the balloon. And the new ventilators, they calculate this by two ways. Deterministic algorithms, which is the case of this ventilator, and some other ventilators, they use AI. Both of them now, we have good literature proving that both are even better than doing occlusion pressures. The performance of these algorithms is already better than using inspiratory pause or expiratory pause. Basically because this is continuous. You have 24 hours a day. You can do an average. This is, you have a sample. Sometimes you have to repeat at least 3 times to be sure. And sometimes the patient reacts. So this is now the future for mechanical ventilation. Let's just understand a little bit how, for instance, this ventilator works. As I told you, this is a deterministic algorithm. So they are showing here the esophageal pressure. Let's go to the screen. It's not the esophageal pressure. What they are showing here, they looks like esophageal, but this is muscle pressure. Muscle pressure is all the dynamic driving pressure produced by the patient. So it's a little bit higher than the swing in esophageal pressure because you are taking into account how much force you are using to expand the chest wall. When you are using an esophageal balloon, you can only observe the force to expand the lung. Here you can see the whole force to expand the lung plus chest wall. So it's a little bit higher than I would see with the esophageal balloon. So this is the dynamic driving pressure driven by the patient. But this is very good because this is, in blue, is the dynamic driving pressure driven by the ventilator. And then I can sum up both. But the ventilator does for us. So the ventilator is telling us that the muscle is 14. The ventilator is doing peak pressure minus PEEP, which is 20. PEEP is 10? 9? 9. So we have 11 of dynamic driving pressure produced by the ventilator. And then if I sum both, we should have 25 or 26. The machine is calculating for us that the driving pressure is a little bit more. This is the static one. Should be a little bit less than the sum of these two, because these two, if I sum this one, minus PEEP, plus the muscle pressure, these two should be a little bit higher than the driving pressure, because the driving pressure here is calculated as the static one, okay? So the difference sometimes is 0, because you achieve 0 flow at the end of inspiration, and the ventilator recognizes this. Also, if the expansion of the lungs is slow, you almost don't have resistive pressures. Okay. This is exactly what I'm showing here. Muscle 14, peak pressure 30, minus PEEP gives you 15. 15 plus 14 is giving you almost 30. But then the static one, in this case, the static one is lower because we had very high inspiratory flows. And then the resistive component is a little bit higher. So the static component should be a little bit less. Which one is correlated with mortality? Both. So you don't have to, but the thresholds are different. When we talked about 12 is static. If we go for dynamic, nobody knows, but something around 16, 17. Okay? This is what I'm showing you here. This is the static. This is the dynamic. Certainly, this is very bad because this is well above 12. And even worse, because I told you, spontaneous is worse than controlled ventilation in terms of lung injury. So how this deterministic algorithm works? It's this sequence of equations, but basically is the equation of motion of the respiratory system, and then you have to apply some filters on top of it. I'm not going into the details, but basically you have, this is the reference signal. This is the raw signal that the ventilator calculates, and then he applies a filter that gets you the red one. And then using this algorithm, then you can provide online this. So let's understand a little bit better the relationship between these values and some common maneuvers like the occlusion pressure or inspiratory pause. Let's do it. Expiratory pause. Can you freeze the screen?
Yes, it's already.
Okay, can you freeze here? With the maneuver. Yes. Look, which is the philosophy of doing the occlusion pressure? Every breath, I have this swing in pleural pressure. And then at one specific breath, you occlude the airways during expiration. It's an expiratory pause. And then your airway pressure has to follow the pleural pressure because there is no way to go. There is a blockage in the flow. And then, then your pleural pressure is going to be instantaneously transmitted to the airway pressure. And then by measuring this swing, you can calculate the pleural swing. Obviously that every time you do this, you can cause an artifact because you promote some reaction of the patient. Yeah, so, but we can, this is why this maneuver has to be performed 3 times at least and is intermittent. So this is the advantage of having this number all the time, 24 hours a day. And I think this is the future, not only for this ventilator, but some other ventilators that use artificial intelligence. Marcelo, would you like to say something else to finish?
So I would like to say thank you to everyone. And our booth, it's in front of here. If you want to see the vent, we can explain how we're doing the calculations. And Marcelo is going to show, we have a survey. And if you have time, please, can you answer our, oh, yes, this one. Thank you very much for your time. Thanks for coming.